All right, I want to take a look at the baked potato problem, which was the big problem that got talked about in the 2017 exam. It's a really nice example, pretty typical example of a differential equations problem. So anyway, t equals 0, we've got this baked potato, and they give us the differential equation here, dH dt, the rate of change of the heat of the potato or the temperature of the potato as time changes. And anyway, they ask us first of all to write an equation for the tangent line to the graph of h at t equals 0. Use this equation to approximate the internal temperature of the potato. Okay, so we don't have, let's say the potato temperature is doing something kind of like this. We don't have the actual h equation, we have dH dt. So the idea here is you can estimate a tangent line, and the tangent line will be pretty close to the actual curve for a while, so we can estimate values that are kind of pretty close to the starting information they gave us. So they tell us a couple of things here. They tell us that h of 0 is equal to 91, so it's got the point 0, 91 on the original curve. And we have the dH dt equation there. So remember, when you write the equation of a line, you can use point slope form. Y minus y1 is equal to m times the quantity x minus x1. Technically, I guess we're dealing with x's and, h's and t's this time instead. So anyway, our y value here is 91. Our x value here is 0. We can kind of fill those in. M, of course, is the slope, and the slope is a derivative. And they give us this derivative equation right here. Now be careful. dH dt will give us the derivative, but we do need to be careful because that is in terms of h, not in terms of t. So that's negative 1/4 the h value. H is 91. Okay, that's the output variable here, minus 27. And then we're kind of going from there. So, so here's my slope, okay? 91 minus 27, I believe, is 64. So negative 1/4 times 64 is negative 16 for the slope, and that's what we're going to fill in here. So our final equation, remember, it's really an h variable. So I'm going to write this as h minus 91 is equal to the slope, and it's really a t variable. So I'm going to say t minus 0, which is just t. So we could say something like h of t is equal to, oh, actually it's not, this is our linear estimation equation, but, so actually, you know what, I will keep the same variables we had originally. I'm just going to write this as y equals, that'll be negative 16x plus 91, and that would be our estimation equation, okay? Again, in terms of the variables in this problem, that'd be an estimated heat and an estimated time, but we'll leave it in that form. All right, use this equation to approximate the internal temperature of the potato when t is equal to 3. Well, that's our input value there, so we can input that. That would be negative 48 plus 91. 91 minus 48 is equal to, I think, 43. So the estimated temperature would be about 43 degrees Celsius. And you should write a little sentence there where you kind of explain that. Let's look at their solution here, and let's see what they say here. Okay, so you can see here they've got that equation. They write it as y equals 91 minus 16t. In other words, a time variable. What they're giving the equation a different name than h, because h is the actual curve and this is the estimation. But anyway, I think we get the 3 points there. Let's go on to part 2. Part 2 asks us to use the second derivative to determine if our answer underestimates or overestimates. So what's happening here is we had a point here on the actual curve of 0, 91, and we don't have the equation of the actual curve. So we went out here to a point at 3, and we found out what the temperature was. And actually, the potato's temperature is decreasing, so maybe our image would be probably more something kind of like this, where we had a point at 0, 91, and then we have a point over here at 3, actually ended up being 343. Anyway, The over-underestimate thing is pretty straightforward. It's about the concavity, okay? If a graph is concave down, that means the actual curve is going to drop below the tangent line, and that would mean the tangent line overestimates. If your second derivative was positive, it would be concave up, and that's a case where the curve would grow more quickly than the actual estimation line, and that means that the estimation line would underestimate, okay? So we really just need the sign of the second derivative, and that's all we're doing here. Now, we need to be careful. They gave us dH dt, okay? dH dt is negative 1/4 times h minus 27, okay? Be careful. H is the output variable, okay? This is like if I had dy dx equals negative 1/4 y minus 27, okay? You can't just take the, use the power rule here to take this derivative because you have an output variable there. This is going to be implicit differentiation. So you may want to multiply this out. That'd be negative 1/4 h plus 27/4 is what we're actually taking the derivative of. Okay, so take the derivative. Derivative of negative 1/4 h for d squared to h dt squared. It's going to be negative 1/4, but I have to multiply by the derivative of the inside function with respect to h, which is going to be times dh dt. This is a constant, the derivative is 0. Okay, now we have the dh dt equation. That's this original equation that we had over here. So technically, d squared to h dt squared, the second derivative would be negative 1/4 times dh dt, which is negative 1/4 h minus 27, okay? And it wants us to see if this overestimates or underestimates. The point that we were using, remember we're estimating from the point 091, okay? So we'd be putting that 91, remember that's an h value, not a t value, in there. And that would be negative 16 times negative 1/4 is equal to positive 4. So that looks like this is going to be concave up, okay? And actually, it's interesting in the answer key here, they don't even put that answer here. They just say we get a value that's greater than 0, okay? So because this is concave up, the tangent line would underestimate. And so, anyway, let's go here and look at their answer and make sure that's right. Okay, so they show the calculation there for the second derivative. And, of course, our h value is always going to be bigger than 27. Oh, that's making the point here that as long as we have values that are bigger than 27, that h minus 27 is going to be positive. And so, anyway, the derivative is going to be greater than 0. It's concave up. That means the line underestimates. And again, you do need to explain it with a little sentence there at the end. All right. Part C, they give us a differential equation here, new differential equation for times less than 10. And they want us to find the expression for g of t. Okay, so notice again, we have the g variable. The g variable is the output variable. We have a y on the left-hand side. So if we're going to take the integral would be with respect to t, and you've got a g over here on that side. So this is a separation of variables problem. We're going to need to separate variables, and we're going to need to work this whole thing out here. So let's see what we've got going on here. All right, so to separate variables, we would start out by multiplying both sides by dt. Get the t's over on the right side. Okay, and then you need to divide. You need to divide by this whole statement. I would probably leave the negative 1 where it is. I think constants are just a little bit easier to deal with if you leave them on the right. So I would leave that negative 1 constant there. But I'm going to divide both sides by g minus 27 to the 2/3. Okay, we have a 1 over here, so it's g minus 27 to the 2/3. Now, we're going to be taking the integral in a minute, so don't leave this in a fractional form, okay? That's not going to be a natural log because it's a 2/3 power exponent. Rewrite that as g minus 27 to the negative 2/3, okay? dg is equal to negative 1 dt. Now, we're going to integrate. Make sure you show that you're taking the integral, okay? We're going to raise the power by 1 here. By the way, there's no derivative of an inside function, so we got lucky. We don't have to deal with the chain rule, but watch for that. Anyway, the new power is going to end up being 1/3. We have to divide by the new power. Dividing by 1/3 is the same thing as multiplying by 3. On the other side, the integral with respect to t is going to be negative t. Don't forget your c value. If you forget that, there's basically nothing you can do at that point. Okay. Now, we need to find the c value. Remember, this function passes through the point 0, 91. I think we still have that information from earlier. Let me go back and check. Yeah. So we should be able to substitute those values in now. So when this is 91, t is going to be 0. Oh, that's nice. T is going to cancel. We're just going to have c over here. So 91 minus 27 is 64. The cube root of 64, the 1/3 power, is 4. 3 times 4 is 12. And it looks like our c value is 12. That is really convenient. Okay, so we can fill all this in now. They do want us to solve for g. So our equation right now is 3 times g minus 27 to the 1/3 power is equal to negative t plus 12. We can divide both sides by 3. Make sure the entire side of this equation gets multiplied by 3. Next, I think we're going to have to cube both sides to get rid of that 1/3 power. And then we can add 27. Looks like g of t is going to end up being negative t plus 12 over 3, quantity cubed, plus 27. Do they ask us to actually find anything? They do ask us to evaluate something at t equals 3. I think we're going to just go look at the answer key for that part. Let's take a look over here and let's see what's going on. So did we get the equation right? 27 plus 12 minus t squared cubed over 3. Yep. And then they substitute in, and it turns out it's 54 degrees Celsius. So a little bit of an overview of the potato problem. Hopefully nothing there that we haven't talked about 40 times by now. So everybody thought this question was crazy hard the year it came up, but hopefully you feel pretty comfortable with it.